So partial f, partial y. So what's going on with x when I'm talking about this?
Constant.
Constant. Not changing. And that means anything that is a function of x is also not changing. We're not specifying what it is, we're just specifying that it's not changing. So this is like the thing earlier on. So so you talk about a word, I can't really remember this stuff, like adiabatic expansion. So that might be volume changing at constant temperature. It'll be the pressure that will be causing it, something like that. That might be right. Something like that. Okay, so if x is constant, what is the derivative of x squared?
X squared.
Nope. 0. Now what we're going to do is, you've got x as a constant times a function of y. We're going to fix the constant x. What is the derivative of y to the power of 5 with respect to y? To the power of 4. Yeah. Now, what's the constant in the third term?
6.
Minus 6. What else? X cubed. And what is the derivative of y with respect to y? 1. Plus, what is the derivative of y to the power of 4 with respect to y? 4y cubed. And we'll tidy this up. So I got, now, there's no particular reason why we write the x and then the y, it's just a convention.
How come you decided that the x is the constant?
Because I'm finding the derivative with respect to y.
Okay, right.
We're going to do the other one in a second.
The other way around.
So I'm going to it doesn't really matter, it's just a nice convention that you put the number first and then maybe the variables probably go alphabetically after that, but it doesn't actually make any, it doesn't matter. We'll do it. Minus 6x cubed plus 4y squared. Now the reason I did the y first is because where the x's are constants, the x's are first. It's easier to...
Where you had the x squared go to 0, how come you didn't do that when it went to 6x cubed?
Because if you've a constant on its own has a derivative of 0,
Yeah.
there's a constant times a function, you fix the constant and differentiate. If you want, you can do a product rule on this,
Yeah.
and when you differentiate the first thing, you get a 0. So you get the first thing by the derivative of the second thing. That's the constant by the derivative of the function plus the function by the derivative of the constant, which is 0. So you're just left with fix the constant, differentiate. Okay. Now we'll do the other one, partial f, partial x.
Should the last one there be cubed and not squared?
Yeah, thanks. Cheers. So this one is y constant. So you're differentiating x as the variable, everything with y is to be treated as a constant. So in the picture we had, you're looking at the slope in the x direction, you're not changing in the y direction. So the y, we're not specifying what it is, but it is a constant. So back here, what is the derivative of x squared with respect to x?
2x.
2x, spot on. What is the constant in the second term? What's the constant here?
5.
No.
Y.
No.
5.
Y to the power of 5. So I might just write, just to get something clear here. This is x times y to the 5. If y is constant, if y is fixed at 2, for example, this is 2 to the power of 5, that's also a constant. So the constant in the second term is y to the 5, so we'll fix that. And then what is the derivative of x with respect to x? 1. What is the constant in the third term?
6. Minus 6, sorry.
minus 6, what else?
Y.
Y. So fix the constant and then differentiate the function derivative of x cubed with respect to x.
18.
3x squared. And what is the derivative of y to the 4 with respect to x?
0.
0. Because y is treated as a constant, so y to the 4 is a constant. I'll tidy that up. So you get 2x plus y to the 5 minus 18x squared y. So there's two slopes. Well, there's infinitely many slopes. You can look in infinitely many directions as opposed to just one. Arguably two on a function of a single variable. You can look at the slope in the plus direction and the minus. And we're just going to look at the slope in the x. X, well, whatever, two perpendicular distances, x and y, I suppose. Okay. There's loads of notation around. So we've seen this one. You might usually see that it could be z as well, partial z, partial x. F1, any idea what the 1 refers to?
The first component.
The first variable, the x. Or you can write f with this little subscript x, we're going to use that one a little bit later on. Differentiate f with respect to x. So this is f2, because you're differentiating with respect to the second component. To compute partial derivatives, all we have to do is remember that the partial derivative of a function with respect to x is the same as the ordinary derivative that you get by keeping y constant.
Could you normally, you wouldn't normally multiply a y, 6y by 3x squared in a normal equation, would you? You couldn't just do that, could you? Normally you'd be bad form, would it?
I don't know what you mean. So when you're looking at this,
the way you tied up the 18x squared y, I suppose I'm just looking back on all this stuff, I don't think we ever would have multiplied a y and an x and done that. Maybe it's the first time I've seen it.
no, it's grand.
Is it alright to do that?
Yeah, I mean,
Across the board, even if you're not doing this, you could.
absolutely.
Okay.
I mean, like for example, I mean, can you forget about the 6 and the 3 for a second?
Okay.
So you could have a square box. Now, what I mean by square box is the one of the three-dimensional, but one of the sides is square.
Okay.
So if the side of the, I'll just draw it. That's what I mean by the square. And then this side, well, the volume is x squared y, no problem. No problem. There might be occasions where, I don't know, I can't think where you would have seen it, but I mean, it depends on what you're trying to do. I mean, it's perfectly fine here. If you've got simultaneous equations and you're ending up with x squared y, yeah, you're in trouble then, yeah. Okay. So, alright, another example. So this time we got a little patch of the surface. I can never remember which one is the x and which one is the y. X, y. I think this is the x and this is the y. I think. Sure, I'll just change it around if they're wrong in here. X, y, x, y, x. Yeah, that has to be right. Right. So this is a little plot of the surface. Z is equal to 4 minus x squared minus 2y squared at 1, 1. So we may as well just, while we're at it, get the output for 1, 1. So f11 is equal to 4 minus 1 squared minus 2 by 1 squared, which turns out to be 1. So we should have a point 1, 1, 1 on this, and you might see it, I don't know how well it printed, but that's this point here. So it's 1 along the x, 1 along the y, 1 along the z. I think you can probably do it here. 1, 1, 1. And calculate the partial derivatives at this point and interpret these numbers as slopes. Okay, so we'll differentiate first with respect to x. What is the derivative of 4 with respect to x? What is the derivative of minus x squared? Minus 2x. And what is the derivative of minus 2y squared with respect to x? 0. Okay, so the slope in the x direction is minus 2x. If we evaluate that at 1, 1, in other words, x equal to 1 and the y equal to 1 doesn't come into play, we get that this is equal to minus 2. We will draw that on the surface in a moment. We'll go again. Well, the other derivative. So differentiate with respect to y. What is the derivative of 4 with respect to y? 0. What is the derivative of minus x squared with respect to y? 0. Because if you're going with respect to y, everything that isn't y, in other words, x is a constant, so if x is fixed, so is minus x squared. So for example, this is like saying what's happening in the y direction. So if you walk along the y direction, what's the x coordinate along here? 1. We might just write this down. So along here, x, I'm just going to say constant. I'd like to say fixed, but just to keep the language going. X constant equal to 1. And along here, what's the y coordinate here? Also 1. So as you walk along the x, your y coordinate does not change. As you walk along the y, your x coordinate does not change. So what is, as you're walking along the y, what is the derivative of minus x squared? It's like differentiating minus 1 squared.
Minus 2x.
No. 0. Along the y, the x is a constant. It's actually, in this context, it's actually equal to just minus 1. What's the derivative of minus 1? 0. So with respect to y, x is a constant, this is just minus 0. What's the constant in the third term?
Minus 2.
Minus 2, so you fix that. And the derivative of y squared with respect to y? 2y. So that's minus 4y, which we evaluate at 1, 1. We'll get minus 4 by 1, we'll get minus 4. And so what you get is that this is the slope in the x direction, the slope of this is minus 2. And the slope of this, although it doesn't look it, is minus 4. Small comment. So if you have a smooth curve and you have a particular point and you zoom in, what does the smooth curve look like? Straight line. That's not bad. Do the equivalent here. Take a point, zoom in. What does the surface look like? Say again?
Flat?
Flat, yeah. The language is it's plane. So you can do the equation of a tangent plane. Now we won't do that, but you could. Okay. Any questions here? Now anything like product rules, quotient rule, chain rules, they all come in if you need them.
Minus 2 is the slope in which direction?
In the x direction.
Alright, and minus 4 is the slope in the y direction.
Yeah. Okay. So we'll see this one needing a little bit of product rule or what have you. Right. So differentiate this with respect to x, where we have this. Okay. So we'll just get cracking on the start of it. What is the constant in the first term?
Y.
Y. So when you're partially differentiating with respect to x, only x is changing, all the y's are constant, so fix the y. What is the derivative of x squared with respect to x? 2x. What do we need to differentiate the second term?
Tables.
You're not lying there. What specific thing?
Product rule.
Product rule. Because it's 3x. Now you can actually fix the 3, but it's easier just to take this to be the u and this to be the v. Now I'll write the u's and the v dashes underneath afterwards, okay? So the product rule says the derivative of a product is the first thing, which is 3x, times the derivative of the second thing. Strictly speaking, now we get away with it, but we won't worry about that. What do you need to differentiate the second thing? Chain rule. Strictly speaking, you do. Now, as it happens with this particular one, if you don't use the chain rule, you get away with it. But we'll try and do it properly. So you've got an outside and an inside. So the chain rule says differentiate the outside. What's the derivative of sine of x? Cos of x. Evaluated at the inside, which is x minus 2y, times the derivative of what's inside. What is the derivative of x with respect to x? 1. What is the derivative of minus 2y with respect to x? 0, because it's all just y's. And because that's 1, you would get away without actually doing the chain rule, but we'll talk about that in a second. So that's the first thing by the derivative of the second, plus the second thing, which is sine of x minus 2y, times the derivative of the first thing. Now, I think we should get in the habit of fixing the constant. What's the constant in u? 3. Not 3x, just 3. And what is the derivative of x with respect to x? 1. Okay, now I'll just do the u's and the v's just so you can see. So this was the first thing by the derivative of the second thing, plus the second thing by the derivative of the first thing. Now we get away without, if you actually didn't use the chain rule, you get away with it. But I just want to show you that. You should be that careful, because if we're going to differentiate, we are going to differentiate. Just up here we'll differentiate the sine of x minus 2y with respect to y, and just show that. You have to be careful. So you understand this is multiplied by 1. So if you didn't use the chain rule, you would have got it right. But just to be careful. So differentiating with respect to y, cos of sine of x minus 2y. It needs the chain rule. The outside is sine of x. What's the derivative of sine of x? Cos of x. Evaluated at the inside, which is x minus 2y. Times the derivative of what's inside. What is the derivative of x with respect to y? 0. We fix constants here. What's the constant here? 2. There's 2. What's the derivative of y with respect to y? 1. So you did need the chain rule there. Okay. Better just safe than sorry. Now we'll tidy this up a little bit. So we'll do 2 by x by y. Now this is multiplied by 1, which doesn't do anything, so we'll just say 3x by cos of x minus 2y. Does anybody want to propose how we write the last term?
3 sines of x.
We'll write it and then we'll say y. So I just want to explain why there's a good reason to do that. So we put the 2 at the front here. It's just a convention. There's no actual reason. Well, yeah, we're just used to it. There's a good reason to put the 3 at the front here. Why?
It's 3 times sinus of what's in the brackets. It's not sinus of what's in the bracket multiplied by 3.
There's a possible ambiguity that you would multiply these together. Because what it is sine of x minus 2y times 3. Now, it should be okay, but there's a possible ambiguity where you think it's sine that these get multiplied together and they don't. So that's why you do that. Okay. Any questions there? Next one. Verify that this function here satisfies the following equation. This is called a partial differential equation. Loads of things in engineering of these. So heat transfer, steady state heat, elasticity, loads of stuff for what we call partial differential equations. Now, they're hard to solve. What we'll be doing is maybe giving you an answer and just check that it is an answer or a solution. Okay, so we'll calculate these two derivatives separately and add them together, see what we get. So we're going to do partial z, partial x. So we're differentiating this. What rule does this need? Chain, not product. It's log of function of a function. So the chain rule says you differentiate the outside function. What's the derivative of log of x?
1 over x.
1 over x.